Okay, so hello and welcome to Information Theory, Lecture 3. Today we're going to continue along with what we've done, or what we've started already, and we're going to start talking about the Kullback-Leibler divergence, Jensen's inequality and its properties, and then we're going to finish off hopefully with the data processing inequality, which is a really interesting and cool theorem that I think has a lot of implications in a lot of different domains. So again, we're still in chapter 2 of our book. We're really in chapter 2 now, in the middle of chapter 2. And also a reminder that homework 1 is due next Tuesday night. There were a couple of questions on Canvas, which I believe all of them were answered. How do you like Canvas so far, for those of you who have not used it? You like it better than Catalyst? I'd be curious to see. I'd like to have your feedback on which you like better. For those of you who've used both, or if you just like Canvas at all. I think I'm kind of thinking it's okay. But yeah, question?
Do you update the other websites?
Well, so our main website, which is really just an HTML website, which I basically edit by hand. I was going to not be putting a lot of the announcements there, and I think I'm just going to put all the announcements on Canvas because A, it's not redundant, and B, everybody gets email whenever I post announcements, and C, it's also pretty well organized in terms of announcements and assignments and other things. So my feeling is that the main website is just going to be where, for example, things like the homework goes, and so that we'll be using it primarily as sort of a stub and as essentially a link with the PDF files, but then the Canvas thing will be sort of where all the information is and where the discussions are, and where the questions are answered. So definitely look to Canvas. The other thing, again, is that you should be receiving email whenever there are updates, so that if you, and I think there's even like an RSS feed for those of you who have RSS readers, I noticed. So that's kind of new. I mean, that's certainly not something, so basically you can have, along with your New York Times RSS feed, the EE514A RSS feed, so you can hear about interspersed stories between the government shutdown continuing and assignment 2 being due, and things like that. So that's sort of an interesting combination of RSSs. So anyway, so I think that answers your question. So anyway, let's move on. So in terms of the review, so we defined entropy. There are a number of different ways of defining it, and how it's in units of bits. And maybe I can somehow turn this off. No, that's not right. There we go. How do we get rid of this thing? Let's try this. There we go. Okay, it's in units of, can be in units of bits or in nats. And as we said, it measures the degree of uncertainty or the amount of information in a distribution, with all the caveats of what information means. And there's low entropy distributions and high entropy distributions and things in between. Basically, when things are low entropy, we're very certain about their outcomes, and when things are high entropy, we're very uncertain about them. We saw the binary entropy function, this is an exact plot of. This is an exact plot of the binary entropy function. So the uniform distribution, 0.5, has the maximum entropy, which, I can't know if you saw that last time, but the maximum entropy occurs at 1. So that's the maximum entropy value. And notice also that that corresponds to log base 2 of 2, which is, and we said log base 2 of the number of possible outcomes is the maximum entropy. So that corresponds with what we talked about last time. In terms of why we use the log, we had Khinchin's theorem, which basically says that if these 3 properties are true, then it has to be of this particular form, where it's some, something proportional to some entropic function, but maybe a different log base. Basically, it has to be, and as we know, the log basis doesn't matter; it's just a constant. All log bases are related to each other when constant on the outside of the log. We had a summary of the definitions. And we also had sort of a Venn diagram, or Venn diagrams that represent information. And these aren't really sets, with the usual caveats of what these things mean. We saw that we can actually describe the relationship between let's This is the marginal entropy of x, the marginal entropy of y, the joint entropy of xy, the conditional entropy of x given y, the conditional entropy of y given x, and the mutual information. That gives us the relationships very easily. Now, what we began very briefly last time was another fundamental definition that we need for this class, which is the Kullback-Leibler divergence, which is a divergence between two probability distributions P and Q over the same alphabet. Or you could just say that they're discrete probability mass functions of the same size over n symbols. And as we will see, there are many important relationships between that and entropy and mutual information. And in some sense, it gives us a way of measuring the distance between two probability distributions, but we want to be careful about the use of the word distance. And on the next slide, we'll talk a little bit more about that. But one possible sort of distance-like function of two distributions might be just to sum up the differences, sum up the squared differences. Okay? But that is unsatisfactory for a number of reasons. Usually, like the squared error, or the average squared error, or something like that, corresponds to sources that are maybe Gaussian distributed. And probabilities range between 0 and 1, and anything that ranges fixed between 0 and 1 is definitely not Gaussian distributed, because, as you know, a Gaussian has non-zero probability mass everywhere, and so therefore there's no point at which it's truncated. There's no point at which the Gaussian is truncated. So any probability distributions live in a simplex, in the probability simplex. Namely, they have to be non-negative, and they have to be they have to sum to 1. And so this isn't really a good distribution. And secondly, we're going to find that our Kullback-Leibler divergence is much more useful in terms of things like measuring compression efficiency if we have the wrong probability distribution, and a number of other things as well. So if you're sort of wondering which you should be at this point, why the Kullback-Leibler divergence, why this particular definition that we're going to give you, if you're wondering why that, in some sense, I can't really sort of give you one single answer until you've sort of taken this course, because we're going to be encountering this over and over and over and over again. By the end of the course, you'll say, okay, well, there are all these reasons why it makes sense to define the Kullback-Leibler divergence in this particular way. Some of the reasons we'll begin to see today. First of all, what is a distance? So let's say that S is any set. It could be discrete or continuous, it doesn't matter. And we have a function that maps from the Cartesian product of the sets to the reals, and it's called a distance if we take any two items from the set x and y. We have that this function is non-negative, and if it's symmetric, so dxy is equal to dyx, and if it's reflexive, so dxx is equal to 0. So the distance of something to itself is 0. So any function that satisfies this property is called a distance. And there's also the notion of a metric. And a metric is the same kind of function. It's a function defined on a Cartesian product between two sets. And so it's a metric if it's also non-negative. If it's 0 only when the two items are the same. So if d of xy is equal to 0, it's only if x is equal to y, and that's called the identity of indiscernibles. The idea being that if x and y are indiscernible in terms of the distance, then x and y are identical. So identity of indiscernibles. And then lastly, second to lastly, there's symmetry. So it has to be symmetric, and it has to satisfy the triangle inequality. So generally, distance need not satisfy the triangle inequality, but a metric must. And a distance must be symmetric, as must a symmetric. And there are lots of other categories as well, like there are things called semi-metric. And we're not going to go into, of course, all of these definitions. There's quite a few of them. But something's called a semi-metric if we replace the identity of indiscernibles by the reflexivity property of the distance. Namely that, so basically any metric is going to be a distance, but not vice versa. Now the question is, where does the Kullback-Leibler divergence fall? Which sort of also describes to you why. By the way, these are sort of formal mathematical definitions that people agree upon. Although you will find in the literature that people make the mistake of calling the Kullback-Leibler divergence a Kullback-Leibler distance. In a number of literature, and actually in well-known literature. But in any event, we're going to call it a divergence. So we have two probability distributions on the same alphabet. And the Kullback-Leibler divergence is defined as as following. Now, the first thing to note is that it's the expected log odds ratio weighted by p. So what we mean by log odds, let's zoom in on it a little bit. Here's the log, here's the odds, here's the log, and here's the expected stuff. So expected log odds. Also note it's not symmetric. It's very easy to come up with constructs and instances of probability distributions where d of pq is not equal to pq. So therefore, this thing is not a metric and it's not even a distance. Sometimes it's called something like a quasi-distance, but we're just going to call it a divergence. Okay. The other thing in terms of its range, when we take limits and look at continuity, we can show that 0 log 0 is equal to 0. That's a well-known mathematical result. And also that p log p over 0 is infinity. So therefore, it's possible. We can actually have instances where d of pq is equal to infinity. So that's a possible value. So it's not bounded. That's one thing. Now, it can be generalized very readily to distributions over vectors of random variables rather than instances of random variables. So now let's say that we have two probability distributions indexed by these vectors. And let's say these are integer vectors or something. So we can then define the Kullback-Leibler divergence in the same way. And again, you get it's basically the only thing that matters is that the probability, you have p log p over q. That's the general form. So we sum over all possible probabilities of t log p over q. Whether it's a vector valued random variable or scalar valued random variable, it's really the same form. So also then, like the mutual information and like entropy, it's really a function of the probability values, not the random variables that the values take on. We could actually completely change the meaning of the random variables. We could permute the probabilities associated with the random variables. We could take, let's say here are the random variable values. Any permutation, as long as it's the same permutation applied to p and q, any permutation when applied to both p and q will yield the same Kullback-Leibler divergence. So again, this is related then to entropy in that sense, in the sense that its measure of sort of whatever it's measuring, we don't know yet, but it's measuring a function only of the set of probabilities, and maybe in this particular case, its correspondence between the probabilities assigned to a given alphabet symbol by two different distributions. Okay. Any questions? Okay. So first of all, let's look at the Kullback-Leibler divergence and the mutual information. So we're going to have two probability measures. The first one is mu1, which is just pxy, and another one, which is mu2. It's based on the same underlying distribution pxy, but it's the product of the marginals. So what do we mean by the marginals? We take this joint distribution here, and we sum out y, and we get the marginal over x. Right? This is like the x marginal. Sometimes, it's important to get familiar with this notation or these terminologies. So here we've got the product, we've got the joint distribution of xy, and we sum out x, and we get the marginal on y, right? So the product of the marginals are the things that go into this distribution here, into mu2. Okay? So if we then look at the Kullback-Leibler divergence between mu1 and mu2, let's zoom in again so you can see better. We just sum over all xy, and we have, mu1 takes the role of p and mu2 takes the role of q. So you have mu1 log mu1 and mu2. So then if we plug everything in, we get the following, which hopefully looks very familiar to you. This is just the sum over all xy pxy of log of the joint divided by the product of the marginals, which happens to be equal to the mutual information. So that means the Koblenz-Leibler divergence, which is in some sense a distance-like quasi-distance something or other thing, is and can be seen as how far away is the joint distribution. This is the joint distribution. How far is the joint distribution from the product of its marginals? If the joint distribution is a product of the marginals, that means that the random variables are independent. So that means, in that case, the joint is not far away at all from the product of the marginals. In fact, the joint is equal to the product of the marginals. And we know from before that the mutual information is 0, which must mean that the Koblenz-Leibler divergence is 0 in that case. So then the mutual information then can be, in some sense, seen as a quasi-distance-like divergence thing. The distance in some sense. And again, I'm being careful about the use of the word distance, but it's a distance-like thing between the joint and the product of the marginal. So it's like how far away is a probability distribution from the independence version of that distribution.
So if you went the other way, you don't get anything special. Like if I do the distance between U2 and U1, then that log term would be flipped upside down.
Well, so if you take the negative, the log term would be flipped, but maybe what you're suggesting is putting mu2 in here, like setting that to mu2. Yeah, so then you get something different. And actually, there are some really interesting behaviors that you get that are quite different if you switch that guy around. Like if you did d of mu2 mu1, you wouldn't. It's no longer the most mutual information, but in some sense, it's also kind of like a distance. But there, it's weighted by the independence, and it's weighted by the independence distribution. So it's a very different weight. So this sort of goes into the definition where we had this wording from before. Let's see if I can find it. It's not very widely used, but maybe it's this one. Information for discrimination. And when we talk about pattern recognition, this definition actually makes sense. That in some sense, it's relative to one distribution, how useful is the other distribution as a discriminator? Or relative to the second distribution, how good is the first distribution for discriminator? And so it can be used in a pattern recognition context. But that's right. It's very different if you. It's not symmetric, so it's very different if you switch the order. So anyway, so the mutual information, the distance between the joint and the product of the marginals. We said this already. Now here's another interesting fact. So this shouldn't be project. It's the product of the marginals. So the product of marginal distribution, for example, px and py, is a projection. It's going to be seen in some sense as a projection of this joint distribution down to the independent distribution. So let's say that you do the following. So you have this Koblenz-Leibler divergence here, and you have d of p prime, where p prime is the original distribution, p is the original distribution, and p prime is some new distribution. And basically what you're trying to do is you're trying to there's lots of bugs here. Okay, it should be min, argmin. This is a pretty severe bug. Surprised I didn't catch that. Anyways, this is equal to the minimum divergence over all p prime such that p prime is factorizable. Okay, so let's say like I've got this distribution is fixed. And I want to find the closest p prime that renders the two random variables independent. It's not too hard to show that the closest p prime that renders the two random variables independent is the one where you take the product of the marginals. I hope that description wasn't too flubbed. I hope that everybody understood it. But this is okay. So let's now define a couple of more mutual information-based quantities and then start relating them together and then using we're going to sort of intersperse a few more definitions with the utility of the Kullback-Leibler divergence. So one thing we're going to define is sort of the event-specific conditional mutual information. And this isn't a term that they use in the book, but I like to use it because it's basically saying the following. Suppose we have three random variables. Okay? These random variables, are not independent. These random variables might talk to each other. They don't necessarily determine each other, but nor are they independent necessarily. And so let's say that one of the random variables has an outcome. So we find out that z is equal to lowercase z. That is an event that can influence the mutual information between x and y. And so we can write that as the mutual information between x and y given z is equal to z, which is right here. Okay. So how do we define such a thing? I mean, basically, it's defined using a conditional distribution where the thing that we're conditioning on is exactly the event that we're interested in. And here's the definition. So notice that it's exactly the same. I mean, if z wasn't there, I'm going to cross it off and then put it back. Okay. So if z wasn't there, we get back exactly the same thing as regular mutual information, but we're not crossing it off. We're actually conditioning on z, so we have to use each of these conditional distributions. Okay. And that is, again, conditioned on the event z is equal to z. So now, what if we were then to take an average over, so I've already said, I lost connection, sorry. I really need to, what I was saying was we uncomment the z, so we're conditioning on z. So I think we've already said all of this stuff, and hopefully you're seeing that. So that when we don't have the z, it's just like the regular standard mutual information 3.7. But then what we want to do is so when we condition on a particular event z is equal to z, that's one event. Well, what about on average over all z? How much mutual information is there between x and y over all z? Well, one way of defining it is to take the average over all the different events z and multiply by how likely that is. And so that's exactly what we do for the mutual information, for this definition of mutual information, which is the usual one that you see. So what we're doing is we're just averaging over z of the event-specific mutual information, which we can write in a number of ways. We can expand it out in this particular way, or we can write it out this way, which is much more common. So this is essentially seen as we're summing over all entries in the joint distribution, and we're taking the log of xy, it's the joint xy condition on z, divided by the product of the marginals xy condition on z. So everybody's conditioned on z. The only thing that's not conditioned on z is that we're sort of summing over everything by the joint probability. So the thing in some sense that measures what we're taking a divergence on is inside the log. It's the ratio of the log odds, but we're averaging it based on the joint. So it should hopefully be very intuitive relative to what we've known before. The other thing you can sort of think of it as is the expected value, according to xyz, of log of 1 over p of z divided by 1 over p of x given y and z. And the way you get that is just by using the chain rule of probability and canceling things out. And what this means is that we can write the conditional mutual information as the entropy of x given z minus the entropy of x given y and z. Now, notice about this definition. So remember, the mutual information between x and y was the entropy of x minus the entropy of x given y. So let's do this cross out and then remove the cross out. So if we get rid of z everywhere, it's exactly the same definition. The mutual information between x and y is equal to the entropy of x minus the entropy of x given y. But all we're doing is really just uncrossing out things, and we're just conditioning on z everywhere. So we're further conditioning on z here in addition to y, and only conditioning on z here. Yep.
What's that E sub p of xy given z? Expected value?
Oh, that is the expected value with respect to the distribution p of xy given z. So it's just the subscript on E is that's the distribution that we're taking the expected value with respect to. Because the only thing Z in this, if we take everything to the right of here, I should write here, so you can see, if I take everything to the right, if I take everything inside of this box, Z is fixed. And Z only varies from the outer sum.
Oh, so that includes the sum over x and y, that expected value.
Yeah, that's right. So maybe I'll parenthesize it to make it a little bit more clear. So if it's the expected value of this whole thing. Is that better? So this whole thing in blue parentheses is a function of x and y, and z is a constant from the perspective of that expected value. And then the way that z varies is from this stuff out here. Okay. So we got a lot of properties to go over. We have things like the chain rule. They're just like there are chain rules for probability, there are chain rules for mutual information. And so here we have the mutual information between this vector from 1 through n and y is equal to the following quantity. So this might be a little bit hard to digest, so I thought that maybe a simple example would be first. Let's just look at this one here. So it's the mutual information between the vector x1, x2, and y. Remember, notice where the semicolon is. The semicolon is separating the x's and the y's. And so we have a 2-element x random variable and a 1-element y random variable. And what that is equal to the mutual information between x and y. So that's how much information y has about x, plus how much information y has about x2. Sorry, the first one is how much information y has about x1, and then the second one is how much information y has about x2 conditioned on x1. So it's kind of like you already know x1, so how much additional information does y have about x2? And that's a very natural property. And what this chain rule does, equation 3.13, it's just a generalization of that, so that x is no longer 2 elements, but it's n elements. And then to show that, it's actually fairly simple. So we just take the mutual information in equation 3.15 and express it as a difference in entropies, which we know we can do. And then we already know the chain rule of entropies, and we apply the chain rule of entropies on both sides. And then there are n terms, and then we combine the like terms. And each of the like terms, based on the definition of conditional mutual information, gives us the conditional mutual information. So we get the chain rule. Okay. Another interesting one is what if you wanted to take the KL divergence between two conditional distributions? Well, by definition, the way we define it is, I mean, there are other ways you might think that you want to define it. You might, so I use the conditioning distribution there. No, you use the joint distribution. And in general, unless you're sort of explicitly doing something else, everything is taking an expected value over the joint. So in this case, you're taking the expected value over the joint distribution of xy of the log of the ratio. And the ratio in this case are the conditional distributions. So another way of writing that might seem to be a little more intuitive is if we say we're summing over, say, x. Well, that's not a good color to use there, is it? Let's use green. Summing over x of p of x and summing over y of p of y given x of log p of y given x over q of y given x. Right, so in some sense, this stuff here to the right is like for a specific value of x, and then we're taking the average value over all x. Average meaning the weighted average. I don't know if that helps. Can everybody read that green stuff? Okay, so thanks to that definition, we also have a chain rule for Kullback-Leibler divergence, which basically says that when we have two joint distributions and we want the KL divergence between the two joint, that's equal to the KL divergence between one of the marginals plus the KL divergence of the conditional. That's like a useful chain rule. I think that the proof is, I think, pretty clear. It's just basically going through the equations and breaking them up, and then using the fact that logs of products turns into sums of logs. The log is something that allows a lot of these properties. The log is something that's going to be useful for that. Now, I want to do something else. So I talk a little bit about convex functions. So everybody, I assume, knows what a convex function is. Everybody knows what a concave function is. If you can never remember what a convex versus a concave function is, so I wrote it like this here. So you can think of a convex function because it sort of looks like this, and a concave function because it looks like this, right? So think of the V as the convex part and the A is the, although you just have to ignore this, you have to ignore the chord, but just get the idea. So there's our convex function right there, right? So you can never forget that now. Oh no, don't tell me I lost. Okay, good, I didn't lose it. Wait, I did lose it? Okay, that's good. Okay, so convex functions are defined thusly. I mean, basically it's saying that the function of the expected value is going to be less than the expected value of the function at the 2 points, at the extreme points. So you have 2 points, x1 and x2. You take the average of the 2 points, and the function of the average is going to be less than the average of the function. Less than or equal to. There are many functions that are convex, and convexity is a huge, important topic. There are books written about it. There's great classes written about it. Marianne Fazal has a very nice class on convex analysis and convex optimization here at UW in the E department, which I suggest everybody take because it's an awesome class. And the kinds of functions that we care about being convex in this class are things like e to the x or x log x, as we will see in a minute. If we were to visualize convex functions, I mean, so this black curve on the bottom is convex, and if we have these 2 points, x1 and x2, so for any value of lambda, you can take the average value of x's. So here's say for a particular value of lambda, and it's saying that the value of the function, which is here, is going to be less than the value of the value of the function, which is green, at the average is less than or equal to the value of the average of the functions at the 2 extreme points, which are x1 and x2. And that's the magenta color. So this thing here being positive is what makes it convex. Now this particular function that I drew is what's called strictly convex, because it's basically saying that the convex inequality is strict, meaning it's not less than or equal to, but it's strictly less than, except when you're at x1 or x2. Obviously, when you're at x1, that's basically saying that lambda 1 is equal to 1, which means that x2 is out of the picture, and vice versa. So it's always going to be equal at the extreme points. But you could have another convex function which, say, looks something more like this, like, you know, maybe it's a polyhedral convex function, where there's a long bit of it. If x1 is here and x2 is there, then basically within that region it's just linear. It's a linear function, locally linear. And so that's not a strictly convex function, although it's convex. So a critically important inequality that we use, and everybody should know, is Jensen's inequality. And basically says that if you take the expected value of a convex function of a random variable, that's going to be an upper bound of that convex function applied to the expected value of the random variable. And that's equation 3.24. So in some sense, this is just an immediate consequence of convexity, right? Because let's say that you had a binary random variable, then the definition of convexity is exactly Jensen's inequality. And what this is saying is that this property is true also for not just binary random variables when you have a convex function, but it's true for n-ary random variables, or multinomials. Okay, the other thing that's important to note in Jensen's inequality is if f is strictly convex, then, meaning that, again, it's only equal at the extreme points, then whenever it's the case that the expected value of f is equal to f of the expected value, so if it is strictly convex and that's the case, then that means that x is equal to e of x. Okay, and what does x equal to e of x mean? That means that the random variable is equal to its expected value. Well, the expected value is not random at all. It's a constant, right? So it's saying that the random variable is equal to a constant with probability 1, which means that x is a constant random variable. So strict convexity along with this guy here implies that you've got a constant random variable. So armed with Jensen's inequality, which I don't think we need to prove, but we're going to prove a couple of other things about information theoretic quantities, is armed with Jensen, we can prove things like the Kullback-Leibler divergence is non-negative. And moreover, that it's equal to 0 if and only if the two distributions are identical. So the only time, similar to a distance, but remember it doesn't satisfy symmetry, so that's why it's sort of like a quasi-distance. One of the things that a metric requires is that if d of xy is equal to 0, then x has to be equal to y. So the Kullback-Leibler divergence will have that property. Remember what it was called? The identity of indiscernibles. It's a very philosophical sounding property name. But anyway, so identity of indiscernibles. So if two distributions are immeasurably different in terms of the Kullback-Leibler divergence, it means that because they are immeasurably different, they're truly identical. So to prove that, we show that the negative of the Kullback-Leibler divergence is less than 0. Now, why do that? Well, just because it maybe makes the proof a little bit sweeter. So let's show. We're going to show the negative Kullback-Leibler divergence is non-positive, and define A to be the support of x according to P. So basically, it's all of the x's that have strictly positive probability. It's called the support. And we start with the negative of Kullback-Leibler divergence, which then gives us the definition, but negated. Now, since the only thing that matters are those x's that have positive support, we can also sum over those. So we sum over x and a rather than all x, since that doesn't change anything. Anything else, because remember, 0 log some other stuff is 0. And then we can get rid of the negative sign by swapping numerator and denominator instead of the log. And now, so what do we use here? How do we get this inequality? Yeah, this is Jensen's. Basically, log, so it's log a convex function.
Negative log is
Negative log is convex. So what is log? It's a concave function, right? So basically, it's the opposite of Jensen. Basically, if it was Jensen and this was convex, this would have been less than or equal to this, but greater than or equal to. But this is less than or equal to because basically, log of the expected value is greater than the expected value of the log. So this is a consequence of Jensen just with concave functions. But by the way, I should mention, it's funny if you go back if you look at the literature in the 1960s and maybe even early 70s. People really, in the mathematics literature, they didn't really use the word concave. They called it concave cup and concave cap. And so you see things like concave, and then literally you have a U or a concave, sorry. Did I say concave? I meant convex. Convex cup, which is really convex, and convex cap, which is concave. But then it was kind of difficult because people didn't have the cap symbol on their typewriters. So you see all these papers where they printed them out without the typewriter and they hand draw the little cap in there off the concaves, but then people would forget which one it was and everything. But then they said, hey, guys, let's just use concave, right? Let's probably, we have enough space in the English language to use a different word. So then hence began concave. Anyway, so now once we look at this, we're back to this proof here. So we look at this, basically the p's cancel out, and we're left with the q's. So we're log of the sum over x's and a. Now remember, a is the support of p, not q. So what can only happen then is if we sum over more elements inside of here, this is going to further up or down the bond, because this can only get bigger. But then if we sum over all of x of q, it's 1. So it's log of 1, which is 0. So therefore, the negative scale divergence is less than or equal to 0. So the Kullback-Leibler divergence is non-negative. Now, there's one other thing which we need to do, is we need to show that it's got equality if it's the identity of indiscernibles property. Now remember, from a few slides ago, I just wanted to put this here again. This is redundant with respect to a different slide. But if f is strictly convex, then the expected value of f equaling f of the expected value implies that the random variable is constant. Z is equal to uz. So let's now use this property. So log x is strictly concave. Okay. There's no point where it's ever sort of linear. So if we have equality in this particular form, let's say this was this line coming from here. This was equation 3.27. And suppose we have equality there, 3.27. So if we have equality, it means then that the expected value of f of z, which is where z is this ratio of q over p, is equal to f, which in this case is log of the expected value of z, which is p of q over p. So that means that z is a constant random variable. And I just realized a typo, but it's not a big typo. This should be q over p. So therefore, z is a constant random variable. So that means that q of x over p of x, it has to be always the same value. So the only thing that's consistent with p and q both being probability distributions is that z is equal to 1 with probability 1, which means that p of x is equal to q of x, meaning that no matter what the value of x is, p of x has to equal to q of x in order to get z is equal to 1. Hence, if p is equal to q, then the Kullback-Leibler divergence is 0 and vice versa. What we proved was the vice versa. It's easy to show that if they're the same, it's equal to 0. This is an if and only if condition. Okay, any questions? So I guess that's really the end of the proof here. Questions? Okay. Now this is going to be very, very, very important. Very, very important. It's starting to sound like Elmer Fudd. It's very important. For example, we can now show that the mutual information is strictly non-negative. I should say, strictly non-negative. It's non-negative. Okay? And it's equal to 0 if and only if the random variables are independent. So the way we do that, let's do the second part first. Suppose we've shown it's non-negative. Then whenever we get an independent distribution, we achieve the 0 value of the mutual information. And it's if and only if, because the only way we can do that is when the two distributions, p of x comma y and p of x times p of y, are exactly identical. So that proves the second part. We need the first part. Now the first part's really easy to prove also, because we just write the mutual information as the Kullback-Leibler divergence, which has to be non-negative. So the mutual information is never ever negative. Nor can entropy be negative. So therefore, that the mutual information can be seen as measuring a degree of dependence between x and y. The larger the mutual information is, the more dependence x and y is. This is one of the reasons why it's so important for things like machine learning and pattern recognition. When you're trying to map from one variable to another variable, let's say that you're trying to map from images to face identities. The mutual information between the images and the face identities of that pattern classifier should be very, very large. And in fact, that's one of the ways of training it, is by having an objective based on the mutual information. So you want them to be as dependent as possible. So something else to remember, putting things into perspective, is this thing where, we have a bound for mutual information, a lower bound and an upper bound. The lower bound is the one we just saw, it's 0. The upper bound, again, is the minimum of the entropy. So the mutual information can never be larger than the minimum of the two entropies of the random variables. We also have this definition of mutual information. So it's either h of x minus h of x given y, or h of y minus h of y given x. So that was the thing we saw before. The interval between the two is the same, even if they're shifted. We saw that last time. And if they're independent, if x and y are independent, then the mutual information is 0. Simply, you can see this by just, again, we've seen it before, but here we say, look, if the conditional entropy of h of x given y is equal to h of x. So that means h of x minus h of x is equal to 0. Because y doesn't change the entropy of x when the random variables are independent. If x is equal to y, so you can have two random variables that are equal to each other. What does that mean? They're just copies. One's a copy of the other. It doesn't mean that each one individually is deterministic. They can still both be random, but what it does say is that if I know x, then I know y. There's no longer any uncertainty in y. So when they're identical random variables, what's the mutual information between them? Well, it's equal to the entropy of x, which is also equal to the entropy of y. And the reason for that is because the entropy of y given x, which is also equal to the entropy of x given y, is equal to 0. If we know y, x is known. And if we know x, y is known. So there's no lingering uncertainty about a random variable if we know something that determines it. For example, like it itself. So this is a very important property. Conditioning can only reduce entropy. This is a really important property. So comparing x with h of x given y. So what it's saying is that when you know something about some random variables and you look at the conditional entropy, that can only reduce your uncertainty about it, on average. When you learn something, you can never know less. So you can never, that's why it's always good to keep learning. Never ever stop learning, because no matter what you learn, you will never know less about anything else that you've already learned. That's what it says, basically. The way to prove this is very simple. Again, using this non-negativity property. Well, in this case, the mutual information is non-negative, and then we can write this as in this way. So then we just put the conditional entropy on this side, and we have that the conditional entropy is less than or equal to the entropy. Now, just one thing to be careful about this. For a particular value of y, if we look at the event-specific mutual information, this might be bigger. One particular value of y might suddenly make x very certain or very uncertain. We don't know. But we're talking about in the average. The average case, when you sum over all y and multiply by the probability of y, it can never increase. It's a very, because so this quantity, remember, is very different than its average. For our YouTube listeners, this quantity is very different than its average. Hopefully we will have YouTube listeners. I always like to say that, my lecture videos get almost as many views as Gangnam Style, but not quite. I haven't quite yet gotten as high hit rate as Psy. But I'm working on it. Maybe if I wrote a song and started dancing around, that would help.
You can put the file. It's your website.
Sorry, say again?
The YouTube file. You need the link for it.
Oh, just go to the top all-time hits, and it's like number 2. It's very easy to find. Haven't you seen them already?
That's the cause of misinformation.
Right, misinformation.
We just search for
Have you gone to the Canvas webpage.
Yeah.
So if you look at the announcements, they're actually listed, and actually they show up embedded into the Canvas webpage. You can actually watch them directly from the Canvas. It's stunning. I'm not doing that part. I just post a link, and then suddenly the video appears. It seems to recognize YouTube links. So are you getting the Canvas emails?
Yeah, actually, did you just post it like for this lecture or the first one? Because when we
Well, I haven't posted it yet for this lecture because I haven't finished this
no, I
lecture.
mean like yesterday or something.
Yeah, I usually post it the evening because it takes a while to actually process. It's actually it creates this like half a gigabyte file for some reason of a lecture. I mean, it's the same slide or 30 frames a second that are being captured, and it does this terrible job compressing it. Because it thinks that it's an action video, and I actually contacted the people who wrote the software and say, no, my classes aren't action videos. They're just static slides that last for minutes sometimes. And they said, sorry, our codec doesn't support lectures. Great. Only action videos. But in any event, to answer your question, if you go to the Canvas webpage, I mean, so have other people received announcements about the YouTube videos? All right, so if you're on the Canvas thing, go to the Canvas thing and look under announcements. And in the announcements, it'll say, Lecture 1 video posted, Lecture 2 video posted, and so far there's only 2 of them posted. So as soon as I finish processing today's lecture, it will say, Lecture 3 video posted, unsurprisingly. So, let's take a break, and I will reestablish connection. Okay, so we reestablish connection now. So we're going to do more bounds and we're going to learn more information about information theory. The entropy of a set of random variables is highest when the random variables are independent. In fact, when the random variables are additive, when the random variables are independent, then the entropy, when seen as a function of a set of random variables, is additive, meaning you just add up the entropies of the individual random variables. As the random variables become more and more dependent, then this becomes a strict inequality. So let's just give you an intuitive question. So suppose it was the case that x1 was a random variable, and x2 through xn were a deterministic function of x1. What would the entropy of the joint be? It would be h of x1, because none of the other random variables offer any uncertainty, any further uncertainty, since they're known. Now, the way to prove that is to use conditioning. The property of conditioning reduces entropy. So we have the entropy of the joint. I should say the way to prove equation 3.33. We have the entropy of the joint, which is equal to the sum of the conditionals. This is like a sum version of the chain rule of probability. But now we use conditioning reduces entropy. So each one of the corresponding terms on the left and the right-hand side of this inequality can be matched, and conditioning reduces entropy. So therefore the sum of the left is less than the sum of the right. There's a two-variable instance. There's another version of this. If anyone's interested in a lower bound, I wasn't going to write this down, but another equation that this is, if you look at the sum over I of h of x of I of x of not I. So what x of not I means is everything except for I. So that guy is going to be less than or equal to. So we can have an upper bound sum form over n, and a lower bound sum form over n. For the entropy. In some sense, the reason why the lower bound, at least intuitive, works is because you're conditioning on absolutely everything. And when you sum up all of these terms on the left, you're in some sense over-conditioning on things relative to what's already being conditioned on. In some sense here, in this joint form here in the middle, the information that x2 through xn has about x1 is being counted in some sense jointly with the information that x1 has about the other one. And here you're sort of countering it, or sort of discounting it, I should say, multiple times. Hence the inequality. At least it's the intuitive reason. So here's the two variable instance of the upper bound. And so when all variables are mutually independent, we get an equality. So if x1 and x2 are independent, then of course then it's equal. Now what about the mutual information versus the conditional mutual information? Do you think we can put a bound between the two? What's your guess? Is one always bigger than the other, or vice versa? So who says the unconditional is bigger, or greater than or equal to? Who says, which means that the conditional is smaller? Who says the conditional is smaller? Who says the unconditional? Who says the unconditional is smaller? We're going to do this by democratic rule. We're more fair than the U.S. government. So, well, unfortunately, democracy doesn't work in mathematics. So it turns out that you can't actually bound the two. And this is important. So it turns out that there are instances where one is bigger than the other and vice versa. So let's first of all assume that x is independent of y given z. Okay? So if in such case, then the mutual information between x and y given z is 0. So in other words, if given z, x and y are independent, then the mutual information is 0. And we can show that in the definition very readily, because basically that means that p of x comma y given z is equal to p of x given z times p of y given z. And that's the thing that exists in the numerator and the denominator. Everything is 1 and everything turns into 0 inside of the log. Or the log turns the 1s into 0s. And this is actually true whenever you have a Markov chain. So if x, y, z is a Markov chain, you've got that x and y are independent given z. Another instance of this is when y is equal to z. So again, you can show this. So that if you know z, if z is given, then y is known, and there's no more information that x can give about y, since everything about y can be known. So the mutual information is going to be 0, because you already know everything about y. And so z can't reduce y's entropy, since y's entropy has already been reduced to 0 thanks to z. Hence, the conditional mutual information is 0 in that case. Okay, so with the conditional mutual information being 0, you can construct an instance where the conditional is less than strictly less than the marginal. So the mutual information between x and y is strictly greater than the mutual information of x and y given z. Because it's easy to construct examples in either of these cases when x and y are, they can even be independent or something. I mean, they can do all sorts of things. Okay, so that's one case. On the other hand, now let's suppose that z is a simple function of x and y. Like, let's say that z just adds x and y. So x and y are random variables. Let's also further assume that x and y are independent, and z just sums them. So they're independent, so the marginal mutual information, x and y, is equal to 0, since they're independent. But as soon as we condition on z, x and y suddenly have this linear relationship. Right? As soon as we know z, like let's say that if we know, let's say x and y are independent, but if we know z, and then say z is equal to 3, okay, so then x is equal to 3 minus y, so deterministic relationship. The mutual information is very, very large. So in general, there's no relationship that you can place. Sometimes conditioning reduces the mutual information, sometimes conditioning increases it. So unlike the entropy function, in the entropy function, conditioning always reduces the entropy. In the mutual information function, conditioning can either reduce or increase it. So here's a little summary of what we know. We've got the entropy, the joint entropy, conditional entropy. Another way of defining the joint entropy. Don't get tricked up by this. Let's write the other one in here. So this is the entropy here. When we look at the mutual information between x and y, that's equal to h of x minus h of x given y, which is also equal to h of y minus h of y given x. So this guy here and this guy here are very different, even though they're sort of summing marginal and conditional entropy. I've seen this many times on tests where people get these things mixed up. It's actually surprisingly tricky to remember the semicolons and the commas and the i's and the h's for some reason. Usually when it's hard to remember these kinds of things, it means that a wrong decision was made in defining them this way. But eventually you get used to it and
Why did they choose the letter H?
Why didn't they choose another H?
No, why did they choose the letter H?
That's a good question.
Is it a chemistry?
I think that might go back to I don't know actually. That's
They use S in physics.
yeah, I think it goes back to the physical, the thermodynamic. But the question is, why did they use the letter H back in physics?
No, I think they use S, not H.
They use S. So then I don't know. Shannon did use the letter H. If you look at Shannon's paper, you can actually Google his paper and you will see the letter H. But in any event, get used to the letter H, even if you don't know why it's the letter H. Okay, here's some more review. We've got the Kullback-Leibler divergence. This is going to be a busy slide. You've got the mutual information. This can be sort of a useful slide to sort of summarize all the relationships. The conditional mutual information, a number of different definitions. We've got the chain rule of mutual information. The conditional relative entropy, the Kullback-Leibler divergence between the conditional distributions. We've got the chain rule of Kullback-Leibler divergence. Jensen's inequality when f is convex, the non-negativity of the Kullback-Leibler divergence, and the identity of p is equal to 0 whenever the Kullback-Leibler divergence is 0, the non-negativity of the mutual information, and the identity equal to 0 when they're independent. Conditioning reduces entropy, that's a super important one, and that when the variables are independent, conditioning doesn't do anything. And lastly, we have this independence bound on H, it's upper bound. And there's another lower bound as well, which I told you about. Okay, so you should know all of these. The reason why I did this slide is for you to have a quick summary of all of them so that you can memorize them. Now, again, we saw this slide before, which was the Venn diagram, and we saw also this slide. So what we're going to do is we're going to generalize this a little bit into, rather than 2 random variables, we're going to use 3 random variables. But before we do that, let's look at the same relationship, but in terms of blocks. So now, basically, height doesn't really matter, other than the height of these blocks are really just more of a carrier signal to everybody. It's really the width of the blocks that convey degree of information. So really, width is the important dimension. Height is just a carrier. The width of the top block, let's write it down here. This is the joint entropy. Okay. This is the entropy of x. This is the entropy of y. And we have that the conditional entropy plus the mutual information plus this conditional entropy equals to the joint entropy. So these things line up. So that might be a nice way. Some of you like, it's basically the same picture as this, except that it's flux rather than them. But now what we're going to do is look at, it's the same kind of picture for 3 random variables, and in doing so define another interesting quantity, which isn't defined at all in the book, but I think it's worth knowing about nonetheless. We've got 3 random variables now, x1 and x2 and 3. There's a joint distribution. And consider the following Venn diagram characterization of all of the different quantities that we've got. So we've got, well, let's do one of them at a time. So this whole thing here is the entropy of x1. Right? This is the entropy of x2. And this is the entropy of x3. Right? If we just take, say, 2 bubbles, we've got exactly the same thing that we saw before. We've got this guy here. Maybe I should do that in a different color, but this football-shaped thing, that's the mutual information between, what I just outlined in green is the mutual information between what and what. It's not on the plot. Yeah, x1 and x2. But now, let's back up a bit. Now we see some other definitions. So now let's say that we're conditioning on x3. So essentially all the information about that is in x3 is sort of known. And the only thing that's left to possibly know is in these other regions. And so we can have, well, of course, when we condition on x3, we can have this guy, which is the conditional entropy of x1 given x3. But more importantly, what this is showing is that the residual mutual information between x1 and x2 is this bit here. So this is this. It's the mutual information between x1 and x2 given x3. So we're conditioning on all of x3, and that's all this stuff here is all that's left over. Okay. And I think, and then the other thing we can look at, of course, is if we condition on both x1 and x2, then this quantity here, does anyone want to tell me what this stuff is? This, what I just did in yellow? Or I'm doing in yellow? What is that? Yes, the entropy of x1 given x2 is 3. Okay, so there's one last region. I mean, by symmetry, we've now defined all the regions. The only thing we haven't yet defined, so by the way, these arrows point this. So like here's an example of, this is the information between x1 and x3, which consists of all of this stuff here. That's what this joint arrow is supposed to convey. The only thing that we haven't defined yet is this guy in the middle. Right, what is that guy alone? And that guy alone is sort of this quantity here, which we haven't defined. Notice that there's 2 semicolons. It's the information among the 3 random variables, x1, x2, and x3. Okay? And we're going to talk about that in a minute. And then the other thing we haven't defined is maybe what could be called a flower, where we use this region. So it's all of this stuff here. It includes that middle region, but it includes all the petals as well. So that's sort of another form of mutual information among x1 and x2 and x3. So that's not this. That's something else. So these 2 additional sort of co-mutual informations about sets of random variables, it's like a ternary relationship of random variables with respect to each other, are interesting information theoretic measures. So let's talk a little bit about them, because I think in the context of this class, one should know about them. So here's our picture again. And we can actually get a lot of these kinds of relationships. So, like, for example, the mutual information between x1 and x2 is equal to the mutual information between x1 and x2 given x3, and, which is this bit here, maybe I'll use a different color so you can see it better. So this stuff here, which is this first term, plus this stuff here, which is the second term. Okay. We can also get that we know from before that the information between x1 and x2 can be less than or greater than or equal to the conditional mutual information. So right now in the picture, it's always showing something which isn't necessarily true, which is why these Venn diagrams can be a pitfall. Because basically, whenever you have a measure in R2, it's always a non-negative measure, right? So you can have a zero measure, which is a point, or you can have a larger measure, which is an area, a non-zero area. But what this is saying is that the mutual information in this picture, this picture is always showing this, right? That it's greater than. But we know that that's not necessarily the truth, so we have to be careful with these Venn diagrams. And actually, there are, if you look at Jung's book, like I said before, I taught from that book before, he goes into strategies where you can actually produce diagrams to prove certain inequalities about information theoretic values. And sometimes these are very useful, but one has to be very careful about it. So you can't perfectly rely on it. So another thing then we can get is that we can define, thanks to this guy, we can define the mutual information among the three random variables as equal to this mutual information minus this conditional mutual information. Which then means that the mutual information among the three random variables might be negative. So how can you have three random variables that have negative information about each other? So it's a very strange measure. But it's a useful measure nonetheless. It's just not necessarily guaranteed to be a non-negative measure. So here's a couple of other ways of writing it. In fact, there's no reason that we have to write it in this particular way. There's no reason we have to write it in the way that we wrote it here. We can also write it this way, or this way, or this way. I mean, one of them is the same. But basically, they're all identical. They all have to be equal to each other. So this is possibly useful. Basically, now we've identified equalities amongst various. Perhaps originally, maybe we'd think, oh, are these two guys the same? And this proves that they're identical, although they don't need to necessarily be non-negative. Okay. What else do we have? We have another form of the inclusion-exclusion principle. This is kind of cool. So we've got, we're including these entropies, then excluding these excluding these entropies, and then including, once again, the joint entropy. Inclusion, exclusion, simple form. So very much like, so it's like a higher order mutual information. This quantity, the negative of this co-information, is sometimes called the ear measure, because it's called for the explaining away residual, and it measures sort of certain discriminative ability in pattern recognition. And this is also something that's used called synergy in neuroscience. And the reason is because of this this definition here. Because basically 2 neurons are said to be synergistic if this quantity is a particular value. And so it's useful. It's been useful in very different, and it's been discovered in various different fields. And also here's another inequality. So you can sort of go on and sort of define these equalities and things. In fact, you can set up linear programs and maybe discover new equalities or inequalities based on these sorts of things. Okay, so I think I'm going to do a problem set on this. So I just had a good idea. At least maybe it's not a good idea. Once you get the problem set, you'll tell me if it's a good idea. Are there any questions about this? So the bottom line about these figures: get some intuition about the quantities from them, but don't rely on them for mathematical proof. Or if you do, be very careful, because it's possible for them to be misleading, I should say. Okay, if there are no questions, Other questions? No. Is that because everybody understands everything? There's a question. Somebody has a question.
No, I said we don't, well, I don't understand everything. I guess that's probably why we don't have questions.
Okay, so what do you have a question about?
No, I just meant that I'm not sure. I don't have an intuition for these things. So I guess.
Yeah, it takes a while. So one of the things, that's a good question. So how do you get intuition about these things? So in particular, like this one. So let me add a page below and sort of do something with this. So remember how we said that the mutual information between x and y was equal to the sum over x and y of p of xy. Oops, I'm making this way too big. Shrink this. This is something I can actually do. Log, sorry, this is getting distracting, so this will be better. Log of p of xy of p of x, p of y. So that's the mutual information, right? Can you see that? Okay, so you can't even see that. So I will move this down. So that's what else will do. Mutual information, right? Now, suppose I wanted to define a measure. Defined to be the information amongst the three random variables. So notice that the numerator, the regular mutual information, is like saying, well, it's an average of a bunch of quantities. And the quantities that I'm averaging is like how far away is the joint away from the product of the marginals. So do you have an intuition sort of from that? It's like saying, well, on average, how close are you to your independence version? What would be a sensible form of doing the same thing but with three random variables? Well, how about something like this? So we're still taking an average. It's quite unreadable. x1, comma, x2, comma, x3. But now we're taking the log again. And if the numerator is the product is the x1, comma, x2, comma, x3, maybe a reasonable generalization would just be the product of the marginals again. Yeah, that's a sensible generalization. So maybe that's a way of measuring such a quantity. And it turns out that that quantity happens to be the measure that we saw in the middle. But there's the other measure. Remember, there's the flower petal measure as well. Remember that one? So that one has a different definition, which is also sensible. Now the question is, which one is the right one to use? It depends on an application. So like synergy was useful in neuroscience, but maybe other ones are useful in other areas as well. So I'll ask a problem set about that. And the other thing is like about intuition, because I do want, I mean, one of the points of all of these pictures is so that everybody does get an intuition about these quantities. It's the way you get an intuition about something is to think about it. So when you're walking down the street, when you're watching this YouTube video, while you're brushing your teeth in the morning on your iPhones, hopefully you will gain new insight and you'll have aha moments. And these aha moments are truly great when they happen because suddenly you say, oh, I see what's going on. And then these are real discrete jumps in cognitive understanding. So here's something to hopefully have an aha moment about in the future, or now maybe, is the log sum inequality. This is something that's very important. We have two vectors A and B. They're non-negative vectors, each of length n. The log sum inequality is the following. It basically says if we sum over AI log AI over BI, it's greater than equal to sort of something where everything compartmentalized, where each of the sums are sort of distinct, where it's just one, it's a value times the log of the ratio of two values. And moreover, we have equality if this ratio A over B is a constant. Now this isn't exactly Kullback-Leibler divergence, but it's close to it because, you know, we're not saying that the A's and B's need to be probability distributions. We're only saying that they need to be non-negative. But this still holds nonetheless. Moreover, again, by taking limits, we still have 0 log 0 is equal to 0, and A log A over 0 is infinity, and 0 log 0 over 0 is equal to 0. By limits and stuff. So that's our convention of those values, whenever those values arise. Now this inequality is very useful and important, and so what we're going to do is we're going to prove it by showing, using Jensen's inequality on the following strictly convex function. So if we take the function f of t is equal to t log t, it looks like the following. I mean, this is clearly convex. This is not a proof that it's convex. You can't. This is called proof by MATLAB. Right? Has anyone ever done that before? Proof by MATLAB. So you want to prove something, you just run MATLAB and do a random simulator and say, well, I sampled 40 billion samples and it was true in all of those 40 billion. And that's fine, except that the space is 400 quadrillion, and you're only sampling this tiny fraction of samples. Here's also a flaw. You know, maybe there's some weird little bump that happens there. And because my MATLAB range was from 0 to 2.5 with a step size of 0.001, maybe that little bump is within that little step size. You never know. So this is obviously not a proof, but indeed, when you take second derivatives or any of the standard methods that you use to prove convexity, this function is indeed convex. But at least this gives you the flavor. Why is this convex? Well, so here's our second derivative. Second derivative, non-negative. Okay. That's the real proof, as opposed to the proof by MATLAB. So now, the log sum inequality. Should we do this? You know what? I'm not going to go through this. This is basically just algebra. Here's the proof. I want to move on to some more of the conceptual things. Basically, what I'm just going to. Here's the actual proof, but I'll just describe it in a sketch. We use Jensen's inequality here. We do a trick where we sort of, this trick here where this is a very, you should go through this in your own time. So we multiply by 1 in the form of bi over bi. And that basically turns this whole thing here into a distribution. And so then we get this guy and this guy being the same thing, which allows us to turn it into the t log t form, which is convex, and so we can use Jensen's inequality. Let me get it. So, okay, let's just look at the definition again so we remember it. That's what's important for the next bit. So here's the log sum inequality. So remember that the compartmentalized version is the lower bound of the uncompartmentalized. What I mean by compartmentalized, I mean this is really just the constant times the log of the ratio of two constants, where the constants happen to be these sums. Here it's actually a sum of a bunch of terms. The sum of the bunch of terms is upper bound of the one single term. Just remember that and then use that for something. For example, what we want to do is show that this is really important. I mean, for example, this is something that actually we're doing this in the order that the book does this, and I can remember the first time I was reading this book, and I was thinking, why do I care that the Kullback-Leibler divergence is convex in the pair? Or why do I care about these convexity things? It turns out that the reason why we care about this is because it will allow us to compute things like the channel capacity function. Let's say we have a massively difficult, horrible channel. Some of the examples we'll see when we compute the channel capacity will be easy to compute analytically, but when you actually have a real channel that you want to analyze, you have to actually compute it numerically. And if it turns out to be a convex function, that's wonderful, right? We can actually compute it. Or what we'll see next quarter when we talk about the rate distortion function, thanks to this property, we can actually also compute the rate distortion function using convex optimization. And that's really important when you want to actually truly understand the profile, this rate distortion trade-off, which we will see. So the importance of this, of the convexity, is that it will allow us to, for real-world problems, compute certain quantities, which we don't know about yet. Nobody knows yet what the rate distortion function is, but we will know about it. Okay, so what does it mean to be convex in the pair, first of all? So let's say that we have two probability mass pairs. So each of these is a complete distribution. Then we can actually take a mixture of this pair. So what this really means is that P is equal to mixture of P1 and P2, and Q is equal to the mixture of Q1 and Q2. So this is a shorthand notation. Please stop me if this isn't clear. So P is a mixture of P1 and P2, and Q is a mixture of Q1 and Q2, where the mixture coefficients are the things that are in common, lambda and 1 minus lambda. That's what this notation means. So then what convexity in the pair means that if you take the Kullback-Leibler divergence between the mixture, that's going to be less than the mixture of the Kullback-Leibler divergences using the two corresponding sets of, or I should say the two corresponding pairs of distributions. It's convex because, again, just like anything, the thing applied to the average is less than the average of the things. And to prove this, we use the log sum inequality. So for each value of x, so this is like a weird notation, but this is saying we take this distribution, this mixture distribution, at value x, and then the log of this distribution over this distribution. We use the log sum inequality. We get this thing. So remember, the thing, this was the one bundle thing, that was the lower bound, and the multiple terms thing was the upper bound. Here's the multiple terms. Each term has the value times log of value over value, and there's multiple terms of this. So that's the log sum inequality. We can cancel out a bit of stuff, like this lambda, and the 1 minus lambda, since they're common. And then we just sum over all of x, and we get exactly this what we want. Using the linearity of the sum to extract out the lambda and the 1 minus lambda. So it's a constant, common to all terms. Okay, so go over that. It's not clear. Now we can set Q1 and Q2 to get convexity just in the P. So like obviously if Q1 and Q2 are the same, then that guy collapses to just Q1 or Q2, or whatever you want to call it. And then we can get convexity just in P. So just in one argument. This property is the basis of what's called the alternating minimization procedure, which actually turns out to be a special case of the EM algorithm, the expectation maximization algorithm, which is also used for the rate distortion function, which you'll learn about in the computation of the capacity function, as I've said. Alternating minimization is something that we'll go over more next quarter. We're not going to go over that in this quarter. But it's a really, really important and interesting form of optimization that's often very, very efficient and useful for convex problems. So thanks to this result, we can now talk and prove formally about the concavity of the entropy function. So remember, concavity with the A. So it's like a upside down bowl. Convex is the kind of bowl you want to eat your cereal in the morning in, whereas concave would not be the kind of bowl you'd want. And by the way, is anyone interested, like in the iPads and iPhones? They always get that wrong. They call it a concave button or something, or maybe so. It's actually it's a convex button. I mean, from my perspective, it's convex, right? Because it's like a bowl. It's not a concave. It's not sticking out. But why do they use the word concave? I don't know. It sounds good. Sounds good to the masses. These buttons here. Does anyone have an iPhone? Android uses concave bowls. Is that right? Does anybody have a smartphone? No. Okay, somebody's got one. Okay, so why is entropy concave in the distribution? So let's write down the entropy and its definition. Now what we're going to do is add and subtract a constant, just log of the alphabet size. So it's log of n, add log n and subtract log n. That does nothing, of course. But what it does do is allows us to write it in a slightly different way. So let's keep the log x there and then subtract out the sum of this. And what we're doing is we're just essentially putting this inside of the sum, but this quantity here, on my pointing, this quantity here, is constant with respect to the sum, so basically it doesn't matter. Right. And we can bring a negative sign in here and turn it into 1 over x. And suddenly it sort of becomes like a uniform distribution. 1 over x is like the uniform distribution. And so therefore, we can then write this as this minus, oh, look at this. This is p log p over some other distribution, which we call it u. It's the uniform distribution. So the entropy is really a constant minus the Kolb-Leibler divergence between p and the uniform distribution. Now this is really important for an interpretation for entropy in a number of reasons. One, we know that the Kolb-Leibler divergence is what? It's convex in p, right? So therefore the negative of the Kolb-Leibler divergence is concave. Secondly, this guy is the maximum value, so this is going to make sure that it's positive. But even forgetting about that for a moment, just think of this as constant minus the Kolb-Leibler divergence. So it's kind of like saying the entropy is like the opposite of the distance between the distribution and the uniform distribution. Right? So it's like entropy is like a similarity measure to the uniform distribution. So if the entropy is going up, it's more similar to the uniform distribution. If the entropy is going down, it's less similar to the uniform distribution. If the entropy is minimal, it's maximally dissimilar to the uniform distribution. And if the entropy is maximum, it means that this guy is equal to 0. P is the uniform distribution, and the entropy value is log of x. It's maximally similar. So you can think of entropy as like a similarity to the uniform distribution. So that, I think, is the deeper intuition. Hopefully, there were a couple of aha moments. Did anyone have an aha moment? Just one? That's 25% of an aha moment? No aha moments. Okay, well, I think that's pretty cool. So there's lots of reasons why we like convexity of the Kolb-Leibler divergence, because it allows us to gain intuition. Okay, so what are some more consequences of this? Well, let's say that we have a joint random variable, or two random variables x and y, and distributed according to p of x and y. Then it turns out that the mutual information is a concave function of p for fixed p of y given x. So what does that mean? So it's like, let's say that we parameterize the mutual information just by the marginal over p of x. So what does that mean, really? So like, we have this mutual information function and it's sort of parameterized by this p of x thing here. And basically, when we plug in different p of x's, this whole expression changes except for, this whole expression is the same except for the p of x part. So we can think of this as, in some sense, the mutual information function here as a function of p of x. Right? Now, since it's a function of p of x, we can think about taking mixtures. Right? And thanks to the Kolb-Leibler divergence and its convexity properties, and its expression of the mutual information, we have the following, that it's concave for fixed py given x. And also the mutual information is convex for a function of py given x for fixed p of x. So again, this is the same idea, except now what we're doing is we're thinking of the mutual information as a function of the conditional distribution, and we're fixing everything here, this expression, except for the conditional distribution, p of y given x. And when we think of the mutual information as a function of the conditional distribution, we can take mixtures of it, and it turns out to be convex. So the key things are this is true, and this is true. Now again, you might say, well, why am I telling you this now? This is only the second week of class. You should be talking about Salvador Dali paintings still, right? Well, no, we shouldn't be. We should be doing this. The reason why is because we're going to see this many, many times, and we're going to see how it's useful. So one should remember these properties, and we'll come back to them. Okay. Okay, so let me just finish this one section, and I want to start. Well, the data, we didn't get to the data processing and inequality today, but there's a little bit more. So let's say that this is an important model of communication. This is I want to sort of leave you in the weekend to think about this idea. So we've got a random source, x, and that's our information source, and it's sent over a noisy channel. So we send a symbol x, and there's a distortion over the noisy channel. The distortion is represented by this probability distribution. We don't know exactly why the distortion happens, but we can characterize it randomly by looking at this probability distribution of py given x. So if it was a perfect unnoisy channel, then x and y would have the same alphabet size, and every time we send an x, there would be a corresponding y that would map directly back to the x. But in fact, when we send an x, there are a bunch of possible y's that could be the outcome. That's noise. It's a form of noise. So the rate of information, how many bits do we get to send per channel use? We will see to mean that will be the mutual information. So every time we send a piece of information, every time we send a message over that channel, which basically means choosing an x, sending in the channel, sending the y. On average, how many bits of information are we going to be able to send? The mutual information. That's going to give us the number of bits we can send on average. And if we want to, say, improve the channel and we want to send more bits, then we want to make the p of y given x less noisy. Now, mixing up x, sort of taking mixtures of x, what this means is we can only increase the information for fixed channel relative to the original mixture rates. Right? That's the concavity property. While mixing up p of y given x for a noisy channel, the fixed course can only reduce the rate of information. Because remember, mixing sort of increases the entropy, and it's convex, so it's going to reduce the amount of information on average relative to the original points of mixture. So this intuition is what's going to sort of help us this will make this very precise, and we're going to use this intuition when we prove Shannon's theorem. Because that's one proof that we are going to go through. It's going to be like a full day to go through that proof. But it's critical to go through that proof. Okay, so I think we're done. Any questions? Okay, so if there are no questions, then have a good weekend. Good luck with the homework. I will be reading the Canvas as regularly as possible. So if you have questions, as you've already been doing, post it there. The homework. And thanks very much, and talk to you soon.